Okay, so before I turn to the mitigation solutions, I want to tell one more story, and this is for Faith. She asked me to include this. We know that science informs how the drivers of climate change act, and that this is more than a century old. Many of you have seen the Mauna Loa observatory graphs of CO2 rising and bumping up and down. It wiggles during the course of the year. I would say that these images, they're iconic images now, are demonstrating not only the impact that we're having on the atmosphere, that is, we've increased by over 40% the amount of CO2 in the atmosphere, but it also shows a kind of breathing. If you look carefully at those graphs, it's not just a monotonic increase, it's a up and down every season. This is the breathing of the Earth, and somehow for me this gives a sense of a living system, a living planet that really is cycling this CO2 back and forth as plants grow, as winter comes. The northern hemisphere has more land area than the southern, so you can see this signature of the Earth breathing the CO2 in these curves. And to me, that's a really vivid metaphor to keep in mind as we look at this, how we impact the planet. The other thing is that atmospheric scientists estimate that about a third of the CO2 that we emit will still be in the atmosphere 1,000 years from today. That means that every time I drive my car to work, which I do, or every time I turn up the thermostat in my house, which I do, there's an echo of that CO2 that lasts in the atmosphere for 1,000 years, for a millennium. It's going to be there. Not all of it, but a bit of it is going to be there for 1,000 years. This is a long-term impact, and that's part of why we can't wait for 100% certainty before we act. It makes sense to treat this as a kind of insurance problem, a risk problem that we need to mitigate early. We have plenty of evidence to do that. But how do we know the CO2 is ours? How do we know that's our CO2 in the atmosphere and in the oceans? So this is the next story, one that I owe to somebody who took a workshop that I gave on climate, and he led me in this direction. So let's talk about doping of athletes with testosterone. Okay, that's a shift in attention. Carbon comes in different flavors. It comes in different isotopes. There's carbon with a weight of 12 and a carbon with a weight of 13 and 14. And photosynthesis likes one form of carbon slightly more than another. So plants give a signature. Even in the atmosphere, there's a mixture of the two different types of carbon. Plants sort of filter out a little bit, and they take on their own characteristic of carbon. And our diet shows that up too. It's not surprising that our diet, our bodies reflect what we eat. Corn actually takes up carbon differently than wheat does. So corn eaters have a little bit of a different signature of carbon isotopes than wheat eaters do, and you can see that. You can do this if you monitor natural hormones. You can actually see little signatures of this. Whether somebody if you look at athletes in the Olympics, you can tell by the samples who comes from the countries where they eat more corn and who comes from countries that eat more wheat. I'm getting somewhere with this. But it basically means that the World Anti-Doping Agency can test for doping by looking at these levels of carbon isotopes in athletes, because if they've been taking artificial testosterone, it's made of soy, and it leaves a signature in their body of the different carbon isotopes that are with respect to a background level. So you can sort of see the corn eaters and wheat eaters, and then you can see testosterone eaters. And the signal shows up very clearly. Okay. Fossil fuels are made of plants. They're made of plants that lived and died millions of years ago and were buried. And therefore, because they underwent photosynthesis, and this photosynthetic process hasn't changed in millions of years, there's a signature of the carbon in plant material that's different from what's in the background of the atmosphere. And we can see over time that this signature in the atmosphere has been changing. And it's been changing in exactly the way you would expect if you were taking extra plant-based material from fossil fuels and you put it into the atmosphere. It's exactly like the athletes. We're doping the atmosphere with a different kind of carbon than was there naturally. For me, this is interesting because it shows once again the point that we're just doing science here. This is not something that people knew for a long time ago. This is a fairly new discovery in the last couple decades or so, that you could do this sort of tracing. But it's just science. And it's just science being applied now to the atmosphere in the same way we apply it to our cell phones or to our anti-doping agencies. For me, that's good to keep in mind.